Remember this moment exactly as it is. In a few seconds, you will leave Earth in your mind and begin a slow journey through the asteroid belt and the dwarf planets. For the next while, you are no longer just a viewer, you are a passenger on a quiet spacecraft that slips out of Earth's shadow and sets a course for the silent stones between Mars and Jupiter. This entire video is your personal flight. We will explain, share, and compare, and you will simply watch these worlds from the front row. Outside your window, Earth hangs in darkness, its night side strewn with faint city lights and slow flashes of storms. The spacecraft glides higher without any jolt or roar, riding soft electric thrusters that push with the steady pressure of a sheet of paper on your hand. The sun is hidden behind the planet for a moment, so that space feels like a dim, quiet room where you can breathe a little more slowly. Your course is simple, outward from Earth's orbit, across the path of Mars, and into the wide ring of rubble we call the asteroid belt. On star maps it looks dense, almost solid, like a wall of rock guarding the outer solar system. The quiet question for this flight is why this region never became a full planet, and what secrets still lie frozen inside its scattered worlds. To follow that question, your spacecraft begins by turning its cameras backward in time. Not in a literal sense, but in imagination, you let the modern solar system fade, and picture this same space about 4.5 billion years ago, when the sun was young, wrapped in a swirling disk of gas and dust that glowed faintly under newborn starlight. In that early disk, countless grains of rock and ice orbited the infant sun like mist in a slow whirlpool. Closer in, where it was hotter, only metals and silicates could survive. Farther out, water and more fragile ices could remain solid. Wherever particles bumped gently and stuck together, they began to grow into pebbles, then boulders, then the first tiny worlds. These growing bodies are called planetesimals, the building blocks of planets. Over millions of years they pulled in more material with their gravity, turning collisions into a slow, hot rain of impacts. In some regions, like the one that would become Earth's orbit, this process ran to completion, and a few large worlds swept up most of the local debris. But between the young orbits of Mars and Jupiter, the story was different. There, the forming giant planets' gravity constantly disturbed the paths of smaller bodies, nudging them into slightly faster orbits, stretching them into more elongated paths, and preventing them from settling down. Instead of one big planet, the region stayed broken into many smaller worlds. Scientists are not yet sure exactly how that balance played out. One idea is that Jupiter's early growth simply stirred the material too much for a single planet to form. Another possibility is that several large bodies started to grow here, only to be pulled apart again by gravitational tugs and slow, grinding collisions over hundreds of millions of years. Whatever the exact path, the result is the same scene your spacecraft is heading toward now, a vast zone filled not with dust clouds, but with ancient fragments. Many are only a few hundred meters across, a handful, like Ceres and Vesta, are hundreds of miles wide. Each one is a fossilised chapter of the solar system's first days, drifting in near-perfect silence. Back in the present, your craft has already left the comforting glow of Earth behind. The moon's orbit lies below you like a pale, curved thread, and the planet that was home a few minutes ago is now only a round memory. At this gentle acceleration, it will take months to reach the main belt, but your mind can cruise there in a single long, sleepy evening. Between Earth and Mars there is mostly empty space. A few small asteroids do cross this region, but the distances between them are larger than the gaps between big cities on Earth's surface. Your spacecraft threads through this openness with almost nothing to dodge, following a path calculated long before you closed your eyes to listen, like a train gliding along invisible rails. As you cross the orbit of Mars, the red planet hangs off to one side, small and distant, its polar caps catching sunlight like tiny shards of glass. You already know that rovers and orbiters study that world in detail, mapping its valleys and ancient riverbeds. Tonight, though, Mars is only a quiet marker on your route outward, a way station you drift past without stopping. Beyond Mars, the first members of the main belt begin to appear in your navigation display. The transition is not a sharp wall. Instead, the probability of crossing an asteroid's orbit slowly increases. Instead of one lonely track around the Sun, your route now weaves through thousands of overlapping paths, like threads in a vast, invisible tapestry. Movies often show the belt as a chaotic swarm where spacecraft must slalom between tumbling boulders. Reality is gentler. Even in the densest parts, the average separation between large asteroids can be millions of miles. Probes like NASA's Dawn mission cruised here for years without any near collisions, guided mainly by gravity and patient course corrections. What does fill this space is time. Over eons, countless tiny fragments have been chipped away by impacts and sunlight, ground down into dust that drifts like smoke. Your ship's hull is tuned to sense and avoid even grain-sized particles, so you feel no strikes, only the same floating calm. Each speck out there is a story, but together they are just a soft cosmic haze. Among all these fragments, a few bodies grew large enough to reshape themselves under their own gravity. They became roughly spherical, smoothing out like drops of wax warmed by a distant flame. These are the dwarf planets, worlds big enough to be round, but not quite dominant enough to sweep their orbits clean. Ceres, ahead of you now, is one of them. Ceres is only about a quarter the width of our moon, yet it holds a third of the mass of the entire asteroid belt. Its surface is dark and dusty, but under that crust scientists suspect a mix of rock, salts, and ancient ice. When Dawn orbited Ceres, it found bright spots in certain craters, likely deposits of salt left behind as briny water slowly evaporated into space. Far beyond Ceres, other dwarf planets circle the Sun on wider, colder paths: Pluto, Eris, Haumea, Makemake, and more. Each is like a different experiment in ice and rock, carried out in the deep freeze of the outer system. Tonight, your journey will touch some of them in imagination, but for now you stay with the first of these round little worlds in the belt. It might feel surprising that we only started calling these bodies dwarf planets in the early 21st century. For most of astronomy's history, anything that orbited the Sun and was not a comet or a moon was simply an asteroid or a planet. The new category reflects a deeper realization: the solar system is more diverse than the tidy list of 9 planets many people learned in school. When Pluto was reclassified as a dwarf planet, it felt, to some, like a demotion. From the viewpoint of this quiet spacecraft, though, the change is more like redrawing a map with better detail. Instead of one privileged list, we now see families of worlds, giants, terrestrials, dwarf planets, and countless smaller bodies, each with its own role in the story of how we formed. That story is why your spacecraft has come here. The largest asteroids and dwarf planets preserve materials older than any rocks on Earth's surface, which have been melted, recycled, and eroded many times. By studying these smaller worlds, scientists are effectively reading a library of stone that remembers the solar system's childhood in fine detail. On board your imaginary craft, this idea takes physical form as instruments gently spin and click. Spectrometers split sunlight reflected from Ceres into its colors, revealing hints of what minerals lie on its surface. Star trackers keep the ship oriented, comparing the patterns of constellations to precise maps while you simply rest and let the data flow past like soft music. Out the window, you can imagine the diversity hidden in these distant points. Some asteroids are rich in metal, the stripped-down cores of bodies that once melted inside. Others are mostly rock, similar in composition to Earth's crust. Still others are carbon-rich, dark as charcoal, holding complex molecules that may have rained onto the early Earth. One possibility scientists explore is that some of Earth's water and organic molecules arrived by way of bodies like these. In the early solar system, impacts were more common, and carbon-rich asteroids could have sprinkled oceans and raw chemical ingredients onto the young planet. If that is true, then quiet stones in the belt may be part of the chain that led eventually to you. As you float safely here in imagination, listening from a bed or a couch, it is strange and comforting to think that the atoms in your bones might once have drifted in a region like this. Iron in your blood, carbon in your cells, oxygen in your lungs could all have passed through the same slow processes that shaped Ceres, Vesta, and countless unnamed fragments. Ahead, Ceres is still too small to see as anything more than a bright star, but your course is already tuned to intersect its orbit. The ship's velocity matches the slow pace of your breathing, steady and unhurried. In the quiet between words, you can almost feel the decades of research that led humans to send real spacecraft here before your mind ever followed. This is only the opening chapter of your flight. You have slipped away from Earth, crossed the orbit of Mars, and traced the outlines of how a missing planet became a belt of relics and dwarf worlds. In the next stretch of this journey, you will come closer to these objects, see how we first discovered them, and watch their quiet surfaces give up more of their secrets. Your spacecraft drifts past the orbit of Ceres as if turning a page in a very slow book. Behind you lies the cluttered belt of stone and dark ice. Ahead, the solar system opens again into a quieter stretch. The sun is a little smaller, its light a little less insistent. Shadows grow longer, colors soften, and the feeling of leaving the inner system becomes unmistakable. Somewhere far in front of you, beyond another wide gulf of space, waits a world of storms so large that Earth would vanish inside them. Around that world, like small lanterns circling a distant lighthouse, are the moons that hold the oceans you came out here to visit. The journey from the asteroid belt to Jupiter covers hundreds of millions of kilometers, but from your seat it feels effortless. The engines whisper in the background, maintaining a steady, gentle push. You do not feel acceleration, you only notice that the sun's glare gradually dims and the stars outside grow sharper, like pinpricks in velvet. As your mind settles into this long glide, you can picture the invisible boundary you are crossing. Somewhere near the orbit of Jupiter lies what planetary scientists call the snow line, the distance from the sun beyond which water could freeze easily in the early solar system. Inside that line, worlds grew mostly from rock and metal. Outside it, ice became as common as stone. It is in this outer realm that the giant planets assembled, sweeping up enormous envelopes of gas and gathering thick rings of moons. Some of those moons remained simple ice blocks. Others, under the pull and stretch of gravity, warmed slightly inside, allowing their frozen water to melt and pool into secret seas. As the spacecraft moves outward, you can imagine the orbits of the inner planets shrinking behind you like concentric rings. Mercury, Venus, Earth, and Mars all fall into a small cluster of circles near the Sun. Farther out, in your path, the orbit of Jupiter slowly thickens into view, a broad band tilted only slightly compared with Earth's, but enormous in scale. Jupiter itself first appears not as a disk but as a brighter star among many. Gradually, it swells and resolves into a tiny globe streaked with bands. Its dominant moon system begins as a mere set of points around it, like grains of dust clinging to a luminous marble. With each passing hour of imagined travel, those points separate and take on identities of their own. You might remember that in 1610, when Galileo Galilei turned one of the first telescopes toward Jupiter, he saw 4 small lights lined up and changing position night after night. He realized they were moons orbiting Jupiter, not stars in the background. That simple observation helped to break the idea that everything must circle Earth and opened the door to a more spacious view of the cosmos. Tonight, your spacecraft is retracing a path that began with that first glimpse. Galileo gave his name to the 4 largest moons, Io, Europa, Ganymede, and Callisto. Each of them is a world. Each has its own history. And 2 of them, Europa and Ganymede, hide oceans beneath their surfaces. A third, Callisto, may also hold a buried sea. You are approaching not just a planet, but an entire miniature system of potential ocean worlds. As Jupiter grows larger in your window, its details emerge. Bands of cream, rust, and soft brown wrap around its bulk. Ovals and streaks mark storms that have raged for years. One vast, reddish storm near the southern hemisphere, so wide that 2 or 3 Earths could fit inside, spins slowly like a bruise on the cloud tops. Yet for all its turbulence, Jupiter feels remote and strangely serene from your distance. The thick atmosphere and deep interior hold pressures and temperatures far beyond anything you will visit tonight. Your destination lies outside, in the cold calm of the moons, where water and rock meet quietly in the dark. The spacecraft's trajectory is plotted to swing you into the plane of those moons, matching their motion so gently that it feels like stepping into a moving walkway. The largest of them, Ganymede, passes first, a big world streaked with icy grooves. Callisto, cratered and ancient, follows, holding its secrets in a shell pocked by eons of impacts. But your path bends toward one of the smaller lights instead, Europa, a sphere of ice just slightly smaller than Earth's moon. As you approach, Europa pulls away from the background stars and begins to show its true face. From a distance, it looks almost smooth and white, like a polished marble. Closer in, patterns appear, long, looping lines that crisscross the surface, reddish-brown streaks wrapped around the globe. They resemble cracks in drying paint or fractures in polar sea ice, yet they cover an entire world. Your spacecraft slows until you are coasting alongside Europa, moving in formation so gently that its rotation seems almost motionless. The view fills the window, a landscape of ice plains, ridges, and dark streaks under the dim light of the far sun and the reflected glow from Jupiter. These lines are called lineae, Latin for lines, a simple name for complex features. Some are double ridges with central valleys, others form tangled networks of broken plates and disrupted terrain. To human eyes, they look like scars, as if the moon's crust has been stretched, torn, and healed again many times. The idea that Europa might hold an ocean beneath its ice first rose from a combination of clues. Measurements of its density suggested more water than rock. Images from spacecraft showed regions where the surface seemed to have broken and refrozen, as though floating slabs had rafted around like ice floes on a sea. Later, instruments that sensed magnetic fields detected signals consistent with a salty, electrically conducting layer inside. You do not need to hold all the details at once. It is enough to know that, beneath the cracked, luminous shell turning slowly outside your window, there is thought to be a global ocean of liquid water. Its depth may be tens or even more than 100 kilometers, wrapped around the entire rocky interior of the moon. Imagine hovering just above Europa's surface. The ice below you might be tens of kilometers thick in places, far thicker than any sea ice on Earth. Yet in other regions, especially near the long fractures, it may be thinner, stretched and warmed by tides until it becomes more ductile, more willing to flow. Those tides are not caused by a familiar ocean, but by gravity. Europa orbits close to Jupiter, and its path is slightly oval rather than perfectly circular. As it moves, Jupiter's immense gravity pulls harder and then less hard on Europa's near side, flexing the moon's interior. Interactions with neighboring moons, especially Io and Ganymede, keep this orbit from settling into a perfect circle, so the flexing continues endlessly. Inside Europa, this constant kneading converts orbital energy into heat. The process is subtle but persistent, like slowly stretching and pressing a ball of clay in your hands. Over millions of years, that heat is enough to keep the deep ocean from freezing solid, even though the surface lies in the icy cold of deep space. If you close your eyes for a moment, you can picture that hidden sea. Above it, the ice shell acts as both roof and blanket. Below it, a rocky seafloor may host hydrothermal vents in some places, where hot water rich in minerals rises from the interior into the ocean. On Earth's deep ocean floor, far from sunlight, similar vents support entire ecosystems. Microbes feed on chemical energy in the vent fluids, and larger organisms gather nearby, forming communities that do not depend directly on light. When scientists imagine life in Europa's ocean, they often think of those earthly vents as analogs. In your mind, you can gently descend from Europa's cracked surface, down through the ice and into the imagined ocean below. The journey is silent. The light fades from pale blue to deep indigo and then to black. The pressure increases steadily, but your imaginary craft adjusts without effort. You reach a realm where there is no natural light at all, only the faint glow of your own instruments. Around you is an expanse of water larger than all of Earth's oceans combined, contained within a shell of ice, turning slowly around Jupiter. There are no waves here, no storms in the usual sense, only slow currents and gradients of temperature and chemistry. In some regions, plume-like upwellings may carry warmer water upward toward the ice, thinning it or fracturing it from below. In others, cold brines from the ice shell may sink downward. Over great spans of time, these exchanges can transport chemicals between the surface and the ocean, a quiet circulation that could help sustain any potential life. Your sensors sweep the darkness. Perhaps they detect tiny suspended particles, gradients in salinity, whispers of heat rising from the seafloor. The details need not be sharp. The important feeling is one of a vast, enclosed sea, shielded from space, yet open in its own three-dimensional way. When you rise back up in imagination to the surface, Europa's ice appears not just as a static shell but as a living crust, slowly migrating, cracking, and healing. The reddish stains along the ridges could be salts and other materials brought up from below, discolored by radiation and time. Each fracture might be a line of communication between the ocean and the frozen exterior. Your spacecraft glides now over different regions, relatively smooth plains where the ice seems young and bright, older areas dense with craters, jumbled zones of chaotic terrain where blocks of crust appear to have rotated and shifted. The variety suggests a complex history of freezing, melting, and reshaping. As you drift over the limb, Jupiter rises behind Europa like a striped, glowing wall. Its presence is constant, filling the sky of the moon with banded clouds and storms. From the surface, the giant planet would dominate every landscape, a reminder of the gravitational dance that powers the hidden sea below. For a moment, you can imagine standing on Europa's surface. The ice beneath your boots is hard and glassy, squeaking faintly. The distant sun is a small, bright point low in the sky, casting long, blue shadows. Above, Jupiter looms so large that it seems almost like a ceiling, its rotation slow but perceptible over the course of hours. Even here, under the cold, near-vacuum sky, you are standing atop an ocean, an entire world's worth of water, layered beneath your feet. That awareness settles into you like a quiet weight. Worlds can appear barren and frozen, yet hide deep reservoirs of potential beneath their surfaces. Your spacecraft's tour of the Jovian system does not end with Europa. As you ease away, the flight path carries you toward Ganymede, the largest moon in the solar system. Ganymede is bigger than Mercury, with its own magnetic field and a complex interior that likely includes several stacked layers of water and high-pressure ice. From orbit, Ganymede's surface looks mottled and varied, bright icy regions crisscrossed by grooves and darker, older terrains thick with craters. Under some of those bright bands and plains, an ocean may lurk tens or hundreds of kilometers below, sandwiched between layers of ice like filling in a layered cake. Ganymede's magnetic field hints at a conductive, probably salty ocean inside. Yet it is a more massive and complex world than Europa, and its inner seas may be trapped beneath exotic ice phases that behave differently from the ice you know. If life exists there, it may live in environments quite unlike either Europa's ocean or Earth's. Farther out still, Callisto circles Jupiter as a quieter companion. Its surface is among the most heavily cratered in the solar system, a record of impacts stretching back billions of years. Beneath that ancient crust, evidence suggests there might also be a subsurface ocean, though perhaps more isolated and less active than those of its siblings. As your spacecraft sweeps through this miniature system, you can think of it as a small archipelago of ocean worlds. Each moon has its own balance of rock, water, and ice, its own internal rhythms of heating and cooling, stretching and settling. Together, they show that oceans are not unique to Earth, nor even to planets. They can belong to moon-circling gas giants, hidden and slow. In the distance, beyond Jupiter's orbit, Saturn shines with a paler, more golden light. If Jupiter is a massive, turbulent guardian, Saturn is its ringed, more distant cousin, surrounded by a retinue of moons with their own surprises. One of them, Titan, holds lakes of liquid hydrocarbons on its surface. Another, Enceladus, is as bright as freshly fallen snow and has revealed an ocean in a spectacular way. Your spacecraft plots a graceful exit from Jupiter's domain, using the giant planet's gravity to slingshot gently onward. The maneuver is smooth and silent from your perspective, a slight change in the pattern of stars beyond the window, a soft shift in the navigation displays. The journey to Saturn begins. This leg of the trip is longer, but your sense of time has already stretched to match the scale of the outer system. Days and weeks condense into a few calm breaths. You rest, carried by momentum and guided by pre-planned course corrections so small you barely notice them. Outside, the darkness deepens, yet it is never truly empty. Here and there, faint streaks of distant comets and icy bodies mark the outskirts of the giant planet's realms. The sun is now a bright star rather than a dominating disk, its light still enough to illuminate your path but no longer overwhelming the background glow of the galaxy. Gradually, Saturn grows from a point to a tiny oval, then to a recognizable ringed planet. Even from far away, the rings are visible, thin and bright, circling the planet's equator like a perfectly aligned halo. As you draw closer, the rings resolve into countless individual particles, ice and rock fragments ranging from dust grains to boulders, each following its own orbit. Saturn's cloud tops are pale gold and cream, with subtle bands and occasional oval storms. The rings catch sunlight and scatter it softly, casting complex shadows on the planet and its moons. Your spacecraft dips into the plane of the rings, careful to thread through gaps and avoid dense regions, though even here the average distance between particles remains vast. Among Saturn's many moons, over 80 that we know of, two catch your attention for this ocean journey. Titan, thickly veiled in a hazy orange atmosphere, and Enceladus, a small, dazzlingly bright moon that glows like a shard of ice. You will visit Titan more fully another time. Tonight, your course focuses on Enceladus, the little moon with the big secret. Enceladus is tiny compared with Europa, only about 500 kilometers across, yet its presence in the Saturn system is outsized. As your spacecraft approaches, you see that its surface is astonishingly bright, reflecting much of the sunlight that reaches it. Few craters mar its face. Instead, it is covered in smooth plains, folded terrains, and fractured regions, especially near the South Pole. You pass over the equatorial regions first. There, the landscape consists of rolling, icy plains and older, darker areas crisscrossed by ridges. The light is cold and sharp, casting long shadows. Saturn hangs in the sky, larger than any moon ever appears from Earth, its rings slicing through the background like a luminous line. The spacecraft slowly reorients, guiding you toward the South Polar region, where the most dramatic activity on Enceladus takes place. As you come into view of that area, you see deep blue fissures slicing across the surface, long, nearly parallel fractures informally known as tiger stripes. From those tiger stripes, something extraordinary emerges, geyser-like plumes of water vapor and ice grains, jetting into space. Against the black backdrop, these plumes appear as faint, ghostly fountains arcing away from the moon before falling back or dispersing into Saturn's ring system. In reality, spacecraft like Cassini flew through such plumes, sampling their composition. They found that the jets contained not just water, but salts, organic molecules, and tiny silica grains, evidence pointing toward contact between liquid water and warm, rocky material at Enceladus's seafloor. For your quiet journey tonight, you do not need every chemical detail. You can simply think of the plumes as breaths of an ocean exhaled into space. Your ship settles into a low pass over the South Pole, positioning itself to skim through the outer fringes of a plume. You do not feel the impact of microscopic ice grains on the hull, they are far too small. Yet the instruments register each encounter, tiny flashes of mass and momentum, whispers from the unseen sea below. From this vantage point, you can picture the structure beneath your feet. A thick ice shell covers a global ocean of liquid water, similar in some ways to Europa's but wrapped around a much smaller moon. Near the South Pole, the ice is thinner, cracked open by tidal stresses. Through these fractures, water from the ocean can rise and escape into space as jets. The mechanism is again tidal heating. Enceladus orbits Saturn within a resonance with another moon, Dione, causing its orbit to remain slightly elliptical. As Enceladus moves closer and farther from Saturn during each lap, the changing gravitational pull flexes its interior. That flexing generates heat, concentrated in the south polar region where the crust seems most fractured. Deep inside, perhaps at the rocky core of the moon, this heating may drive hydrothermal activity. Water seeping into the warm rock would be heated and chemically altered, then rise again, carrying dissolved minerals and gases into the ocean. When that water finds its way through fractures to the surface, it bursts out as plumes. Imagine, once more, descending in thought beneath the ice. You pass through layers of cold, rigid crust, then into slightly warmer, more ductile ice. Below that lies the ocean, a global, salty sea a few tens of kilometers deep, spreading under the entire crust, yet venting most actively near the South Pole where the fractures connect water and space. The ocean is dark, like Europa's, but perhaps somewhat warmer near the vent regions. Tiny grains of silica, formed by interactions between hot water and rock, drift slowly upward. Salts and organic molecules mix into the water. Temperature and chemical gradients form, creating potential energy sources that life, if it exists, could exploit. In Earth's mid-ocean ridges and hydrothermal vent fields, microbes colonize such gradients, turning geochemical disequilibria into food. On Enceladus, any analogous life would likely be microscopic, slow-moving, and deeply adapted to its environment. It might not be widespread or abundant. But the mere possibility that an icy moon the size of a small country could host living ecosystems in its hidden sea is enough to reshape how you think about habitability. Rising back toward the surface, you imagine following a parcel of water as it moves through the ocean, is drawn into a fracture, and erupts into a plume. For a short time, it arcs above the moon as vapor and ice crystals, glittering in the weak sunlight. Some of that material falls back as snow, gradually resurfacing Enceladus and keeping it bright. Some escapes into space, feeding a faint, diffuse ring around Saturn. Your spacecraft, for the purposes of this quiet journey, has instruments sensitive enough to trace that cycle. It maps the density of particles around Enceladus, tracks the faint cloud of material in the E-ring of Saturn, and connects them back to the vents at the South Pole. In your mind, a simple picture forms, a loop of water from ocean to plume to ring and back, a moon-sized water cycle that never once involves open air or sunlight. Comparing Europa and Enceladus, you can feel both the similarities and the contrasts. Both are icy moons with subsurface oceans heated by tidal flexing. Both likely have seafloors where rock and water meet, perhaps in hydrothermal settings. Both show signs of water reaching or approaching the surface, whether in the form of plumes, fractures, or chaotic terrains. Yet Europa is larger, with a thicker ice shell and a deeper ocean, subject to stronger radiation from Jupiter and perhaps more complex interior dynamics. Enceladus is smaller and more fragile, its ocean closer to the surface in some regions, its plumes spectacular but confined to a limited area. If Europa is like a deep, global sea encased in a strong vault of ice, Enceladus is more like a mountain lake that has cracked open, spraying jets through the snow. Titan, which you glimpse only briefly on this pass, adds another layer to the story. As your spacecraft's orbit takes you near it, you see a thick, orange haze obscuring the surface. Instruments that can see through that haze reveal rivers and lakes, not of water, but of liquid methane and ethane, carving channels and filling basins. Yet beneath Titan's crust of water ice and hydrocarbon-rich surface, models and gravity measurements suggest another hidden ocean of liquid water mixed with ammonia. It lies deeper and is more insulated than the oceans of Europa or Enceladus, perhaps less influenced by direct tidal heating, yet still a substantial potential habitat. You do not linger at Titan tonight. Its complex mixture of chemistry and climate could fill an entire journey of its own. Instead, you note it as a third example of a moon that likely holds a hidden sea. In the space of a single giant planet's family, you have now met at least 2, and probably 3, ocean worlds. As the tour of the Saturn system continues, your spacecraft passes other moons, Tethys, Dione, Rhea, each a frozen world with its own peculiarities. Some may harbor smaller or more uncertain reservoirs of liquid water within. The impression builds slowly. Oceans are not rare accidents. They are features that can arise in many different settings, provided there is water, gravity, and a source of heat. You can let this idea sink in while you watch the rings flicker by. They are not solid, but composed of uncountable individual particles, each orbiting according to simple physics. Gaps and waves in the rings are sculpted by the gravitational influence of moons, forming patterns that are intricate yet predictable. The entire system feels like a grand, slow choreography of ice and stone. In the same way, the existence of hidden oceans follows from straightforward principles. Ice conducts heat poorly, so once a moon forms with enough water and an internal heat source, liquid layers can persist beneath the surface for very long times. Tidal flexing, radioactive decay in rocks, or even the lingering warmth of formation can all contribute. Over billions of years, such oceans may come and go, freeze and refreeze, migrate inward or outward, but they are part of the natural repertoire of what a cold, watery world can become. Your spacecraft's path now begins to arc outward again, lifting you slightly above the plane of Saturn's rings and moons. From this vantage point, you can look back and see the entire arrangement: Saturn in the center, rings spread wide, moons on various orbits, some closer in, some distant and slow. Among them, you know, are at least 2 confirmed oceans and 1 strongly suspected. Farther off, in your memory of the Jupiter system, Europa, Ganymede, and Callisto continue their own orbits, each carrying its inner seas along. Together, these 6 or more worlds form a small sample of a much larger pattern. In the outer solar system alone, there may be dozens of bodies with subsurface oceans, from dwarf planets like Pluto to minor moons of Neptune. You do not need to catalog them all. It is enough to feel how the simple picture you may have carried, one blue planet with oceans and several dry companions, has expanded. Water, in its various phases, is widely distributed. Oceans can hide under ice, not just splash across open surfaces. Habitability is a layered concept. Your spacecraft coasts in silence while you assemble these impressions into something more intuitive. You see, in your mind's eye, a map of the solar system where every known or suspected ocean is marked not by bright colors, but by soft glows inside the silhouettes of moons and dwarf planets. Each glow represents a volume of liquid water, maintained over millions or billions of years. In this map, Earth's ocean stands near the center, open to the sky, reflecting sunlight and clouds. Around it, at greater distances, are the enclosed oceans: Europa's deep global sea, Enceladus's smaller, vent-fed basin, Titan's buried ammonia-rich layer, Ganymede's stacked, high-pressure waters, Callisto's possible brine, and the likely oceans of distant dwarf planets you will touch on later. The image resembles a constellation drawn not in stars, but in invisible seas. You can let this mental picture linger, unfocused but steady. Each point of liquid water is like a quiet, potential cradle for chemistry, a long-running experiment sheltered inside ice. As you hold that constellation of oceans in your thoughts, the spacecraft gently reorients for the next phase of its journey. You are still on the same quiet vessel, still resting in the same familiar position, watching the slow turning of the outer system. Only now, the map you carry of these ocean worlds feels fuller, more detailed, and more alive. And with that map quietly glowing in the back of your mind, you are ready to let your view widen again, beyond a single star and its moons, to the greater galaxy where similar processes may be unfolding around countless suns. You are still on the same quiet spacecraft, floating in that familiar seat while the map of ocean worlds you formed in your mind slowly glows beneath you. Nothing around you is hurried. The outer solar system turns with its usual patience, and you remain a passenger, simply watching as the idea of hidden sea settles into something steady and calm inside your thoughts. From this vantage point, it is natural to let your view expand beyond a single star system. You can imagine other suns scattered through the galaxy, each with its own retinue of planets and perhaps its own families of icy moons. The chemistry that made oceans possible here arises from clouds of gas and dust that exist all across interstellar space. In the cold darkness between stars, simple molecules form on the surfaces of tiny dust grains. Hydrogen and oxygen meet to create water, while carbon joins with other elements to build more complex compounds. Observations with instruments like the Hubble Space Telescope and large radio arrays have detected the spectral fingerprints of these molecules in distant clouds light years away. Later, when those clouds collapse to form new stars, much of that water survives, frozen into grains that swirl in protoplanetary disks. Infrared telescopes and millimeter-wave observatories have seen bright bands of water vapor and ice in these disks, circling newborn suns. The same basic mixture that fed the growth of Europa and Enceladus appears to be present wherever planets are forming. Space observatories that study exoplanets, such as missions dedicated to watching stars for tiny dips in brightness, have revealed that planets are common. Many of them are larger than Earth and smaller than Neptune, a range that may include worlds rich in water. Although we cannot yet map their interiors, models suggest that some could hold deep global oceans beneath thick atmospheres or ice layers. When you imagine all of these systems at once, the galaxy begins to look less like a sparse place and more like a vast experiment in how water, rock, and light can be arranged. Some configurations yield dry, airless stones. Others give rise to hot gas giants or frozen dwarfs. And some, perhaps many, may produce the quiet, shielded oceans that resemble the ones you have visited in this journey. Returning your thoughts to Earth for a moment, you can feel how central its own ocean has been to your existence. The seas on your planet store heat, move nutrients, and carry currents that soften climates. They dissolve gases from the air and exchange them again, linking the deep ocean to clouds, rains, soils, and the slow growth of life across continents and shorelines. Over geological time, Earth's ocean has changed in composition and extent, sometimes more acidic, sometimes more alkaline, sometimes partially covered in ice. Yet through these changes, it has remained a persistent reservoir where chemistry could explore possibilities. At some early point, that exploration crossed the subtle threshold into biology, though the exact steps remain hidden in time. When scientists study hidden oceans on Europa or Enceladus, they carry with them lessons from Earth's long history. They know that life can thrive far from sunlight, that it can use chemical energy at vents or in rocks, and that it can adapt to pressures and temperatures quite different from those on the surface. These observations guide their questions about what might be possible elsewhere. They ask whether European tides could keep seafloor vents active for spans of time comparable to major eras in Earth's history. They consider whether Enceladus ocean has enough dissolved minerals and gradients to support stable ecosystems. They explore how stacked oceans on Ganymede or isolated seas on Pluto would differ from the more open, vent-rich environments on other moons. Because direct sampling is so difficult, scientists lean on methods that extract maximum information from limited data. Spectroscopy parses light into colors to reveal compositions of ices and gases. Radar sounding can probe below surfaces by sending radio waves that reflect off buried layers. Careful tracking of spacecraft motion allows gravity fields to be mapped, exposing variations in internal structure. Future missions are being designed specifically with ocean worlds in mind. One spacecraft, called Europa Clipper, is planned to make many close flybys of Europa, carrying ice-penetrating radar, cameras, spectrometers, and a magnetometer. Its goal is to refine our understanding of the thickness of the ice shell, the depth and salinity of the ocean, and the ways that surface and interior exchange material. Another mission from the European Space Agency, named JUICE, short for Jupiter's Icy Moons Explorer, is tasked with studying Ganymede, Europa, and Callisto in detail. It will use instruments such as laser altimeters and radio science experiments to investigate their gravity fields, surfaces, and potential oceans. Together, these missions aim to turn the broad strokes of current models into sharper, tested pictures. Farther in the future, concept studies for probes to Enceladus imagine orbiters that could sample plumes with more sensitive detectors, or even land softly near the tiger stripe fractures. Engineers sketch designs for drills, melting probes, or small submersibles, while carefully weighing the challenges of sterilization and power. None of these ideas is simple, yet none breaks the known laws of physics. For Titan, a rotorcraft lander named Dragonfly has been proposed to fly through the thick atmosphere and visit multiple sites on the surface. Its instruments would study organic chemistry in the dunes and perhaps near ancient lake beds, helping to clarify how complex molecules assemble in a world where water is mostly frozen and hydrocarbons flow as liquids. Indirectly, this also enriches our picture of hidden oceans below. From your comfortable position in the ship, you can imagine these future explorers as distant cousins of the craft you are riding in now. They will not move quickly on human timescales. Years will pass between launch and arrival, and even then, measurements will trickle back in patient streams. The story of ocean worlds unfolds over lifetimes, not days, matching the slow rhythm of cosmic processes. Meanwhile, telescopes on and above Earth continue to survey exoplanets, refine measurements of disks around young stars, and detect more detailed spectra of planetary atmospheres. Some of these data reveal water vapor high above alien worlds, hinting at underlying reservoirs. Others show clouds, hazes, or unexpected molecules that will take time and careful modeling to interpret fully. As all of these efforts advance, the central question behind your journey remains beautifully simple. Given water, energy, and time, how often does chemistry become biology, and biology become something capable of shaping its environment in noticeable ways? We have one confirmed example in Earth. The icy moons and distant oceans you have visited and thought represent many opportunities to look for a second. If such a second example were ever found in a hidden sea, even if it were only a sparse community of microbes, the implication would be profound. It would suggest that life is not a singular accident, but a natural outcome when conditions are right. If, on the other hand, all these oceans prove sterile despite favorable chemistry, that result would also be powerful, highlighting something unusual about Earth's path. Either way, the search is carried out with patience and humility. Instruments are calibrated, models improved, and data cross-checked before claims are made. This cautious approach may feel slow compared with the speed of imagination, yet it is part of what makes the eventual conclusions trustworthy. Your quiet flight tonight mirrors that patience, taking its time as it moves from one idea to the next. You might notice how thinking about distant oceans gently alters the way you see your own life on Earth. Daily concerns that occupy your mind shrink a little when placed against the backdrop of moons circling giant planets and seas that have turned in darkness for spans longer than all of recorded history. This is not to dismiss those concerns, but to give them room within a larger, calmer frame. The same water that fills your cells and flows in your veins has likely been part of clouds, rivers, glaciers, and ancient seas many times over. It may have existed as ice in space before the solar system formed, or as vapor in a collapsing nebula. In this way, you are physically linked to the oceans you have imagined on Europa, Enceladus, and beyond, through the shared circulation of molecules over cosmic time. From the window of your spacecraft, Earth is not visible in detail anymore. It is a small, pale star somewhere behind you, lost among many others. Yet you know that on that distant point, oceans move under clouds, continents drift slowly, and living things breathe in rhythm with sunlight and seasons. It is one world among many possible ocean habitats, but it is the one that currently holds your resting body. As the narrative attention of your journey turns gently back toward that body, you can notice the contact points between you and wherever you are lying or sitting. Perhaps there is the feeling of a pillow under your head, a blanket over your shoulders, or the subtle weight of your hands resting. Gravity holds you to your small world just as surely as it holds moons in their long orbits. You can sense the slower, more local rhythms that continue regardless of what distant spacecraft are doing. Air moves in and out of your lungs in an easy cycle. Your heartbeat maintains its quiet tempo. Muscles release tension bit by bit as you allow them to, just as frozen crusts can ease and crack when internal heat rises. There is no need to force any of this, it unfolds on its own schedule. While you rest, your planet is turning. Somewhere, morning light is touching the surface of the ocean, elsewhere, night is deepening over mountain ranges and cities. High above, satellites trace their paths, and far beyond them, probes continue their long, silent arcs through interplanetary space. None of these motions ask anything of you in this moment. You are free simply to lie here and notice or drift. The spacecraft in your imagination keeps gliding too, following its smooth course through the outer system. It passes above rings and moons, crosses the orbits of dwarf planets, and moves outward until even the sun is just one bright star among many. The cabin around you remains warm and still, a small pocket of familiarity traveling through a vast, indifferent, yet quietly beautiful expanse. If your mind is still alert, you can replay pieces of the journey whenever you like. You might revisit the cracked, bright face of Europa, the shimmering plumes of Enceladus, the hazy skies of Titan, or the distant hints of oceans on worlds like Ganymede and Pluto. Each memory is like a small window you can open and close at your own pace, without needing to cover every detail at once. If, instead, your thoughts are becoming softer and more fragmented, you do not need to hold on to the structure at all. The science, the missions, and the maps will wait in the background like books on a shelf. You can let them blur as you drift closer to sleep, knowing that the outer solar system and its ocean worlds will continue their orbits whether or not you are awake to picture them. At some later time, new spacecraft will reach Europa and Ganymede, new instruments will scan Titan and Enceladus, and new telescopes will refine our view of planets around other stars. Those events will unfold over years and decades. For you, lying here tonight, it is enough simply to know that this careful exploration is underway and will continue long after this recording ends. The journey you have taken in this series of thoughts began on the familiar surface of Earth, beneath a sky lit by a single Sunday. It carried you past the orbit of Mars, through the asteroid belt, into the domains of Jupiter and Saturn, and around icy moons whose oceans lie hidden from direct view. It then widened to include more distant dwarf planets and the broader context of a galaxy full of stars. Along the way, you watched how water, ice, and rock can combine to create protected environments in places once considered too cold or remote to matter. You saw how missions like Galileo and Cassini, and planned explorers like Europa Clipper, Juice, and Dragonfly, turned faint signals into detailed stories. You connected those stories back to Earth's own deep oceans and to the water that sustains you. Now the flight is slowly circling back toward quiet. Your spacecraft continues into the dark, but the narration can soften and thin, like clouds dissolving at the end of a long day. You are free to let go of individual facts and names. What remains is a simple awareness that the universe is full of hidden seas and long time scales, and that you have spent a gentle while drifting among them in imagination. Down on your small blue world, you are resting while distant moons orbit in silence and unseen tides move in alien oceans. You can stay with the feeling of that connection for a few more breaths if you like, or you can let your attention narrow to the weight of your body and the softness of the space around you. There is nothing you need to do next, nowhere else you need to be right now. If you choose to sleep, you can imagine the spacecraft dimming its lights as it glides farther into the dark, leaving you in a cocoon of quiet. The instruments keep gathering data in the background, like distant thoughts that no longer demand your focus. If you choose to remain awake, you can simply rest in this calm state, knowing that the story will still be here whenever you want to return to it. And if, on some future night, you ever want to drift through these alien oceans again, this journey will be waiting for you. The icy moons will still be circling their planets, the hidden seas will still be turning beneath their shells, and you will still be able to take a seat on this quiet spacecraft, close your eyes, and let your thoughts follow the slow, soothing paths of worlds in the dark.